Hello, guys. This is Mr. Leshin. It's good to be back here again. This is SS1 class, physics. We started the topic in the previous class. After we finished our surface tension, we started elasticity. And we discussed a lot about it in the previous class. And we are going to be extending it to the final part of elasticity this week, which is the final topic in our, and this time, our scheme of work. Well, let me do a quick recap on what we did in the last class. We talked about elasticity. Before we go to elasticity, we talked about elastic material. That is, these are materials that are able to regain their shape or size after being released from a force that has expanded them or compressed them. They regain their shape. While elasticity is the ability or tendency of a material to retain its original shape after being compelled by a force to extend or to compress. So after that, we went to in elasticity, we talk about extension. That is, this is the extended after a force is being applied to a material, it increases. When it increases from its original size, that is the extension. The length by which it increases is the extension to the original length. We talk about Hooke's law, which says that provided the elastic limit is not exceeded. What is elastic limit? That is the point at which a force is applied beyond this point. An elastic material will lose this is elasticity. If is the maximum point at which a material can accept or contain a force. Beyond this point, then it loses its elastic material, then it becomes plastic. That is, it doesn't regain the original size again. So Hooke's state that provided the elastic limit is not exceeded, the extension is directly proportional to the force. Meaning, the more the force, the more the elastic material expand. The more the force, the more the elastic material compress. Compression and expansion. These are the effects of the force on the material. Let me talk about the Young modulus. So the Young modulus is the ratio of the tensile stress to the tensile strain, where the tensile stress is the ratio of the force to the cross-sectional area dealing with our spring. We talked about that last year. And the tensile strain is the ratio of the extension to the length. The extension to the length. So on this week, we want to be looking at that. We want to look at the work done in the force, the work that the force did to stretch a material. The work done in the force in stretching a material to calculate the energy is related to the work done. We can call it work done in this case, and it's also the energy. So that's how we calculate the energy in elastic material. So before we come, I'd like to share with you the notes. So we go with the notes and saw some examples under it. So this is the notes. Yes, I can say we extend energy in elastic material. This is the final topic in our scheme of work for the third term for this section as a whole. So look at it. Let's take a look at this notes. Energy in elastic material. Consider a spring or rubber whose unstretched length, that is the original length, is L centimeter. Take L centimeter. Let a maximum force F, a force F, cause an extension, cause a displacement or extension of the spring by E. That is, E is the length by which it extends or expands. The increase in the original is compelled, attracted by the force, caused by by the force. Consider a spring or rubber whose unstretched length, that is the original length, L centimeter. Let a maximum force for F cause a displacement or extension of the spring. That extension is given as E centimeter. The force in the wire has increased from 0 at point P in the stretch or normal position P to F at P. That is, when the force is applied to the material, there's an change in position of the wire. That is, there's an increase in the length of the wire. That is, from a point of original length to another point of extension. Full stop. Work is done. Work is done by the force. Work is done by the force in stretching the spring through the extension. So the work done is what we are looking at in this week's topic. That is how to now calculate this work done. You can see the work is done by the force. Yes, the force are compelled on the material to extend or compress it. There's a work has been done in that effect. So the work done, W, is now given by the product of the average force. The average force, if we are saying average, that is the initial plus the final force divided by 2, we give you the average force, and the displacement or extension, we call it, let's say extension, that is the product of the average force and the extension. Mathematically, this is it. Mathematically, average force is what? Initial force plus final force over 2 from the word average. So average force is given as what? 1 over 2F, where F is what? The force. Where F is what? The force. So work done as stated in the note says that it is the product of the what? Average force and the what? Extension. That's why we have what? Average force times what? E to give you what? 1 over 2 Fe. 1 over 2 Fe, where F there is the force and E is the what? Extension. This is how to calculate the work done in what in elastic material. This is the formula to use. F 1 over 2 Fe. 1 over 2 F is what? Average force and E is the what? Extension there. Therefore, given the work done to what? The product of the what? Average force and the what? Extension. So this work is equal to the energy stored in the elastic material. I told you earlier that the energy and the work done is the what is the same in the what in elastic what material. We call from Hooke's law. We say F equals to what? Ke. F equals to what? Ke. If you have F equals to what? Ke here, say F equals to what? Ke from this situation here, from this Hooke's law, F equals to Ke. So now replace F to be what? Ke in this what? Formula here, that is 1 over 2 Fe. Replace F as what? Ke. You have what? 1 over 2 Ke, that is Ke is what? F multiplied by E equals to what? 1 over 2 Ke square, where K in the previous topic I told you is what is the stiffness of the material or the what force constant or the what force provided anyhow it comes in your question. You know is what they can call it the stiffness of the material or they can call it the what the force constant. So in another place where you're given question overall to calculate the work done, whereby force is given and extension is given, you can easily use average force times what extension to calculate your work done. But in the case whereby you are given the force constant and you're not given the force, you are given extension. So this is the formula to use. So these are the formula. These are the two formulas by which you can calculate the what energy in an elastic material or the work done by the force in a what elastic material. So let's take these two examples. One example. So look at it. Example: a spiral spring, a material is compressed. Because I told you, the force can either what compress it or extend it. So this one says a spiral spring is compressed by 0.02 meter. The extension is what? The compression is what? 0.02 meter. That is, you can call it what? An extension also. So calculate the energy stored in the spring. If the force constant I told you earlier, K can be equal to what? Force constant or stiffness of the what? Material. So if the force constant is what? 400 Newton per meter. 400 Newton per meter. So you have to calculate what? The energy stored in the what? The spring. The force required, the work that has been done for the force to compress the material by what is 0.02 what meters. Which formula is there to use now? First, you consider your parameters given. You are given your extension E to what is 0.02 meters. You are given the what force constant to the what 400 newton per meter, and you are asked to calculate the what the energy stored in the what in the material. So the formula to use is we also what easily what 1 over 2 Fe, 1 over 2 F times what E. That is in the next slide I show you here. Energy stored is in we are given force constant that is 1 over 2 Ke square rather. That is energy stored in the spring is given out 1 over 2 K times E square, where K is what force constant given as what 400 Newton per meter, and E is given as what 0.02 meters. So apply the parameters, inside the parameters into the formula, you have what 1 over 2 times what 400 times what is 0.02 square, 0.02 square. So pick your calculator. If you solve this through, that is 400 times 0.02 square divided by 2, you have what your work done to what 0.8 joules. 0.8 what joule. This is a way by which it is as simple as this. It's a way by which you calculate what the energy stored in what elastic material, the work done, and the force to stretch or to compress or what a material. So let's use the other formula to solve another question. Let's take example 2. Calculate the energy stored in a 2-meter long copper. That is, the length of the material is what 2 meter. Originally is what 2 meters. Copper wire of cross-sectional area of 0.5 millimeter square. 0.5 millimeter square. If a force of 50 Newton is applied to it, take Young modulus equals to Young modulus of copper equals to 1.2 times 10 by 11 Newton per meter square. This is another dimension by which you can calculate what the energy stored. Now you relate the first three parameters. You are given the original length to be 2 meters. You are given the cross-sectional area to be 0.5 millimeter square. You are given the force to be what 50 Newton, and you are given the Young modulus to be what 1.2 times 10 by 11 Newton per meter square. Look at this now. You have to calculate the energy. What is the formula for energy? One, you can use 1 over 2 Fe, that is force times what extension, or 1 over 2 times what the force constant. 1 over 2 force constants times what extension squared. Now looking at this now, you are given the force. The force is what 50 Newton, and you are not given the extension. So from these parameters, you know that Young modulus is given as what stress over what strain, whereby you calculate that is FL over what AE. From Young modulus, you can easily calculate your find your what extension, and when you find your extension, you can easily what multiply it with the what the force to get your what energy stored. But first and first is that you have to find the what extension. Extension in the formula for what energy here. Extension is the what are missing parameter. So let's look at the solution. This is how you go about it. First, you have to write out the parameter that this energy stored is equals to what 1 over 2 Fe. And from Hooke's law, we have F equals to what 50 Newton given. L, the original is given as what 2 meters. The Young modulus is given as what 1.2 times 10 by 11. And area is given as what 1 is 0.5 times 0.5 millimeters squared. That is the area will have what 0.5 times 10 to the power minus 6. We should understand the mathematics. If it's ordinary length in meters, it would be what 0.5 times 10 to the power minus 3. But in areas, it's a square. Is what 0.5 times 10 is about what minus 6. So first thing you get the formula for what Young modulus. So this is what formula for Young modulus. That is Young modulus originally is what y equals to what FL, that is force times length over what extension times what cross-sectional area. Make E the subject of formula. You have what E equals to what FL over Young modulus times what area. Given that F is given as what 50 times what 2. F is given as what 50 times 2 divided by what 1.2 times 10 by 11, which is Young modulus times what 0.5 times 10 by minus, which is the what area. Insert all the parameters into this formula. You have what 100 divided by what is 0.6 times 10 by minus 0.6 times 10 by what 5. Divide through, you have what 1.67 times 10 raised to power minus 3 meter. Extension is what 1.67 times 10 raised to power what minus 3 meter. So if you've gotten the extension, then it's easy to now apply that what energy, that is E. This is what E equals to what 1 over 2 F times what E. 1 over 2 F times E. That is the energy. 1 over 2 F times E. Given that F equals to what 50 Newton from the question, and from our calculation from Young modulus, we are able to get our extension to be what 1.67 times what 10 raised to power 3 minus 3. 1.67 times 10 raised to power minus 3. So if you solve through, you have what 1 over 2 times 50 times 1.67 times 10 to the power minus 3 equals to what 0.04 joules. I would like you to pick your calculator and cross-check these calculations very, very well. Why 0.04 joules? So this is how to calculate the work done in what in the force in stretching a what a material or compressing it, in expanding a material or compressing it. So this is how to calculate the energy in an elastic material. And recall what elasticity is. Elastic material, the elastic limit, yield point, breaking point. Hooke's law, you have to be able to what state your Hooke's law very, very well, and know that the condition of Hooke's law is that the elastic limit must not be what exceeded. Provided the elastic limit is not exceeded, the extension by which the force that causes an extension is proportional to the force that brings about the what extension. So this is that is what we'll be looking at in the topic energy in an elastic material, and with the calculation sent and attached to the online note as an assignment, which requires of you, I will require you using Young modulus to get some parameters to be able to what solve your work done. But with this explanation, I believe, and with the note online, you'll be able to solve any questions attached to what energy in elastic material. I would like you to go over the note again from the beginning of the topic, that is elasticity. You look at elastic material, you look at the elastic limit, you look at consider the what tensile stress and tensile strain very, very well, and know how to calculate your Young modulus very, very well. Thank you and have a nice day.